A common problem that we solve in physics is the inclined plane, where you have an incline, and so it's inclined at some angle, and then you have an object that is sliding down this inclined plane. For now, since we haven't really talked about friction yet, we're going to assume that our surface is frictionless. We will deal with the inclined plane that has friction before too long. The inclined plane is weird because it's at an angle, which means that the normal force is not vertical in this case. It also acts at an angle. So the forces acting on this are just gravity, which of course is mg, and then normal force that acts at this angle here. For the inclined plane, it is useful to rotate your coordinate system. And the reason for that is because this box, or whatever it is only going to move along in this direction. The normal force is perpendicular to that, and then when we add friction, it will be parallel to the direction of motion. So it's handy to rotate your coordinates so that your x is going this way, your y is going this way. So x is along the incline and y is perpendicular to the incline. It just makes the math easier. And yeah, just trust me on that. Now, so this gravitational force then becomes a little bit difficult to break down into components. If it's at an angle, this is our y direction, this is our x direction. We have a y and an x component here. Because of some similar triangles here, so this, if we extended this down, this would make a right triangle here. So then this would be 90 minus theta. Okay, this right here is also a right angle. And so if this is 90 minus theta, then this angle, again, is theta. Okay, so this y component then, since it's the angle adjacent, since it's adjacent to the theta, this y component of the gravitational force is actually related to cosine theta. Okay, if that's not clear, I can talk to you about that individually. So so we write Newton's second law in both directions. In the y direction, we know that the sum of our forces is 0. And the reason we know that is because this block isn't going to jump off the plane, and it's also not going to fall through this surface. So in the y direction, it's not accelerating. In fact, it's not moving at all. And we know the forces that are acting. We have a normal force going in the positive y direction, and then we have a component of the gravitational force, which I've just described as being related to the cosine of theta, acting in the y direction. In the x direction, we have, this is mass times the acceleration, and that's, in this case, in the x direction, we have a component of the gravitational force, now mg sine theta. This is a common thing that's going to happen in our force problems. We're going to say that the sum of the forces is equal to 0 or ma, depending on what's going on, and then set that equal to just writing out each force individually and adding them all up. So get used to setting up problems this way. So in the case of the inclined plane without friction, the acceleration, we can see that the mass cancels out, and the acceleration is just a component of gravity. So if you're on a frictionless plane, it doesn't actually matter what the mass of the object is. They'll all fall down at the same rate, just as they do when the acceleration due to gravity is, when gravity is the only thing accelerating it. In the y direction, we can see that we get our normal force is equal to mg cosine theta in this case. So that's one thing that happens in an inclined plane. We could also have an inclined plane where there's an additional force acting. So you've got a box, and let's say now in addition, this box is being pushed. There's a pushing force, there's the gravitational force, and there's a normal force. Now I'm going to give you some data. Let's say the mass of this box is 22 kilograms. Actually, that's really big. 2.2 kilograms. The mass of the block is 2.2 kilograms. It's being pushed with an upward force of, I don't know, say 12 newtons. And I want to know what is the acceleration of this block. So we can write in the y direction, we know that the sum of our forces is still 0 because, again, this block isn't going to jump off the plane, it's not going to fall through the plane. And in the y direction we have a normal force, we have a component of gravity, mg cosine theta, which is, that's it. And in the x direction, we have mass, acceleration, not 0. And in the x direction, we have an mg sine theta. That would pull this down the ramp. And then we have the pushing force pointing up the ramp. Yep. And from this, we can calculate, we can figure out what the acceleration of the object is going to be. We can go ahead and find the normal force too. So from our y equation, we know that our normal force is just mg cosine theta, which is 2.2 times 9. Oops, I didn't give you the angle. Let's say this angle is 27 degrees times cosine 27. So in this case, the normal force would be 2.2 times 9.8 cosine 27. In this case, our normal force is about 19.2 newtons. Newtons are the units that measure force. I probably should have mentioned that at the beginning. And then in our y direction, we can rearrange and see that our acceleration is mg sine theta minus the pushing force over the mass. So that's 2.2 times 9.8 sine 27 minus 12 all over 2.2. And if we punch that in, minus 12 divided by 2.2, that gives us an acceleration of minus 1.005, so about minus 1.01 meters per second squared. The minus, well, we call down the ramp to be the positive direction. So that means the acceleration is 1.01 meters per second squared up the ramp. Okay. Now we didn't know which direction this object was going to be moving because we didn't know whether this pushing force was stronger than the gravitational force, or that component of the gravitational force or not. But it just came out in the math. As long as we keep our signs straight, we don't have to know what direction anything's going to be in because when we calculate it, the sign of our answer will indicate to us what direction that force or that acceleration or whatever is going.